So, welcome back to this live coding session of me trying to implement a HTTP server from scratch. Last time we left off trying to construct responses, and we dug our hole into the wrong direction, trying to construct some string. But we might rather write to the socket directly. So this is something we want to do today. And what we also want to do is probably change our hash map a little bit such that we get it a little more performant. I thought about it, and there are probably some things we can do. Okay, so let's start with the response construction. And here, I think we didn't implement the okay, so I think we introduced an HTTP header list. But I think, this would also need an allocator. I think we might actually not use it and use the HTTP header map instead. So that would mean we hope we didn't. Okay, so we don't have these things in here yet. So let's look at this. Delete, yes. Delete, yes. Okay. So when constructing a response, we just iterate through the entire thing, and we have to also take a look at whether the current entry is present in the HTTP header map. And I think, yeah, a bucket tag. So this is now not a bucket, HTTP header bucket. Header map, what was it called? Buckets. So this is the current bucket. This is the buckets. Current bucket. So this has a length. But okay. So we probably want the capacity here. So let's say HTTP header map. Header map is equal to response header map. So this is the current bucket. I think that also has, yes. Okay, so this, and now we have to check if the current bucket tag is not equal to initialized. Can continue. And otherwise we just go through this. I mean, it would be more efficient if it was a list. We could theoretically make it a list. So let's to do. Consider making this a list in the future. Okay. So we get a file descriptor. What we can do now is open that file descriptor. I guess openfd. Something we can do. No. Open file descriptor Linux. Let's just open. I thought I had seen something like this. Open at. Great. I bet you. I saw it somewhere. HTTP server. See GitHub. I think it was this one. And it gets a file star. Open. Send response. FD open. FD open. Okay, so this is nice because using this we can actually write to the socket directly without having to allocate some string and increasing the size of the string every time. And so he used fprintf. We don't want to use that. We probably want to use, so fprintf probably uses something like fputs under the hood. So let's look at the related things. Open. Close. Yeah, so I think we can just use the FD here and mode, which is obviously right. So right, I think is the correct thing. Okay. And our file star, file stream, socket stream, do this, and if this is not set, if we cannot open the file, then we return -1, and otherwise we just fputs, I guess, or fput. Is it fput with no, fputs? Puts, fputs. Can we, so write, fwrite probably is the thing we are looking for, that we can provide a size. I mean, in the end, we could also not use strings. Yeah, we have to use strings in the header map. No, we have to use strings. Because we are directly referring to that memory of the socket we read from. Const void pointer. Okay. So what n writes nmemb items of data. Each size bytes. Okay. So this would mean that we have to put. So we replace this. This is also a void star. Yes. The size, which is just the size of a car, and this. This number equals the number of bytes. Okay. So this also can fail. Array size. Okay. If this fwrite does not equal HTTP version prefix length, then we want to return -1. So HTTP version 1.1 length. Yeah. I mean, we could just. I don't like this string formatting. HTTP. Let's see, HTTP. Oh, wrong one. HTTP.h. Yeah. Shall we implement a formatter? So we won't do it right now, and we just use HTTP version 1.1. Version 1.1. HTTP version 1.1. So this is a void star, size of a car. And this obviously should be equal to HTTP. If this is not equal, HTTP version 1.1 length. Okay. So there might be a reason. fwrite. And this is the size of a car. And obviously this has to be equal to the reason.length. So if there's a reason, we just put it in there. We also put character return line feed in here. Wrong one, size of car. I think it was like this. Yeah, the size and then n members. And we forgot to put the file stream, which is the socket stream. Socket stream. Socket stream. So this line is somewhat long. Let's just split it up. Okay. 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 Maybe we just make the code a little bigger such that someone watching can actually see it. Okay. So we put a carriage return line feed. And we put all the headers, carriage return line feed. And I think at the end of the headers, we have to put another carriage return line feed. Is that right? So I think the body, we have to pull up the RFC again. So let's see, message, start line, carriage return line feed. Then, okay, so yeah, it's like this. Fwrite, the size of a car, and then the socket stream. This of course has to be equal to size CRF link. Okay. Okay, so in here we say fwrite, 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 fwrite. The size of a car again, or this is just one, but okay, we put it there. And the socket stream, and if it's not equal to the field name length, then we return -1, just like that. Then fput c should be a thing. Fput c, it's just double colon. So fput c, this obviously takes, what does it return? What does it return? Return value. Return the character written as an, okay. So if this is EOF on error. Okay. Ooh, so this is standard IO. Does standard IO allocate? Probably. if we are just using the operating system primitives, we probably have to manage that. Does fwrite allocate memory and see. I think we just stick to it for now, but it's not optimal how we do it here. Yeah. So this is an fwrite. Fwrite, if fwrite, blah 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 blah. Also fput c. This takes the character and should return it's not equal to this. Okay. We could define a constant that is no void star here. Right. Size of car, socket, stream. We could make a macro here. Field value, length. Field, no. This is obviously the CRLF length. Same thing here. Does not equal CRLF length. And fwrite such pointers. No, this is the size of a car, the socket stream, and the message body dot length. Let's just put a to do here and consider moving away from fwrite and rather handling this on your own. Okay. I mean, this is a very convenient way of doing it. Okay, so handle the get request. So obviously we have to assemble a response here. So if these, let's start with the get request, or should we start maybe with a post request? So post request, if there is none, we set the result. And also if we give a reason, if we provide a reason here, we would have to allocate memory, which would not be so nice. Yeah, well, I don't know. So let's look at the struct again. So status code, reason. Let's just put the reason. Oh no, this is the status code. This is equal to null. This, the version obviously is 1.1. Header map and message body. The header map should already be filled. Right. I mean, the version and the header map should already be initialized. Okay. So we put these two things and then we return something. Return. I mean, why would this fail? I don't even know why this would fail. I think this is even a void. So let's make it a void. Okay, so if I think about this, maybe we put a to do here in as well, and revisit the hashing function as it involves a lot of modulos which are inefficient. Okay. And also an HTTP header map where we say to do consider using hashing by multiplication and a table size that is a power of 2. Okay, this was something I was curious about, and we might do this. So yeah, this might be more efficient. Okay. So if it has both of them, we have a problem. If it has transfer coding, if it has a content length, and else also this should construct a bad requests. So if it has, okay, let's just say this also applies. So if it has a content length, then we should parse this content length to a number. So stir to U32. I don't know. Let's call it something like this. Of the content length. Let's call it string to U32. And then we have a result, content length, int. And with this one, we can read out the message body. So, but we don't know. So the message body is a string, if I recall correctly. So it has to be in the HTTP parsing. Yes, it is a string. So we have to assert somehow so I suppose if the content length int is greater than the content length. Oh no, it was a string. No, it was the message body. So request message body length. So let's call this the message body. To request message body. When the message body length is less than this, then we also have a problem. Let's just call this. Okay, so we probably don't need this return here. Okay. So it's at the moment it's only if it has a content length. So yeah. So otherwise we want to read this. We obviously didn't implement this here. We could make a shortcut and just use A to I. No, this is standard lib, okay. So string to U32. Probably we should put something like this into a string library. Yeah. Okay, so if we have something, we just say printf. Or we want to say the result status code is equal to 200. So okay. The reason is result reason is equal to null, and we want to insert into the header map a content length that is result header map, probably a reference. I think it was 2 strings. And these we now would have to allocate. I mean, should we use this? I mean, which headers should it be arbitrary? Or should we just I mean, at this point we would have to allocate memory to allocate a string. I mean, we could also declare some string memory and use that. But obviously the I mean, when the response was sent, when we send the response, we can obviously deallocate this. So how do we do this? We could put I mean, okay, if we would insert this into here and send the response, then we would not have to. Then we would not have to allocate because it was on the stack already. But the header map also would be, oh. The header map obviously would be kind of bad. Would be in a bad state if we did that. Init the response. So maybe we would need some memory. At least to put the content length into here. I mean, we could provide some stack allocator here. We could allocate a so we would have to allocate some memory and put the content length. I mean, we could for this particular case, we could hard code it. But we would also need to, so we probably need this here. We would need an HTTP, probably content length. Yes, so we already have this. So this is a content length So field name, content length, header name. This is content length, header name, content length, header len. So this content length header, content length header name, and now we would need the value as well. Content length header value, or content length name, content length value. We might already have this string here in here somewhere. Yeah, content length string. So we could insert the content length string here. So we already have that, and the value obviously now has to be some string that represents some number. So u32 to string, something like that. So string so also how large should this buffer be? How large should it be? So we would have to allocate some memory. In this case, it's just 0, so we would actually have to allocate a car. And the string heap. And so no other allocations here. The string heap, just the size of a car. I think this is it. So this is the car star 0 length. I mean, in this case, we could also hard code it into HTTP because it's very common. So maybe here, car star, this is 0 length 0 const expr string 0 length 0 length string, and this is equal to the 0 length and the 0 length size of -1. So in this case, we can just hard code it. 0 length string. Okay. So we insert this, and I think that's it. And also this is probably a reference when we insert. Yes, it is. So okay, so now there will be a lot of errors. Pretty sure. So let's for now just ignore the string heap here. Init HTTP response. Okay, so we obviously don't have an init for this. HTTP. What? No, it's not the init for the response. It's for the response.header map. HTTP header map. And which way was it? Oh, it needs a size. Okay. Also a reference to the arena. So this is a const string. So cast it to a string star. Okay, string to U32. Maybe we ignore it for now. Okay, so fput c HTTP version 1 length. Conversion from char star to known scalar. Okay, so the reason is just the char star. I doubt that. I mean, it could be a char star. Yeah, let's just say it's a char star, isn't it? If the reason is present, then we just put it in there, and we just say fput s. Fput s non-negative number on success. So if this is less than 0, so this obviously doesn't work. It is just the reason. It takes a char star. Okay. Fput s. Fput s. Reason is a char. No, it's a char star. Okay. HTTP version 1.1 length. Version 1.1. HTTP version 1.1 length. What? Zero length. Oh my goodness. Zero length. This is a car star. Okay, that it compiles. I don't know if this is any good. So in handle post request, we should do something. So let's go into GDB and break okay. So let's break at 206. Let's run this and let's curl -x post localhost 8080 and let's put it, give some data. Hello world. Should hit that breakpoint. Let's get dash. Request method. Let's just print the entire request. So let's see if we have something in here. Okay, so we actually have something in here. So this is kind of weird. Dot header map dot buckets at 128. So yeah, okay, it's the same. So next, maybe it did work. No, didn't work. So it kept the connection alive. We should have written this response. Oh, we forgot to close the file descriptor. So fclose and the socket stream. And this returns an int. UF if this is equal to EOF, return -1. So break 206, run HTTP1 subversion. Okay. unsupported. I think it was 1.1. And we probably didn't insert a space. Is that the problem? That there are no spaces? Probably this is the problem. Okay. So far right. Now there should be a space. Okay, so now there should be a space. That means we could in our, yeah, this is hacky, but whatever. Okay, let's make it verbose. What it gets. Couldn't connect the server. What? Ooh, okay. Erno, what's that? So let's go into write response. Okay. So we write a character return line feed. Breaks 74. HTTP version prefix HTTP slash G11. I mean, it looks correct to me. Let's break at 87. No. Break del 3. Break at 87. No, continue. Next. Message body. Okay, so this is just uninitialized. Okay, so that is obviously bad. Why is it? Oh no. It's uninitialized. Oh no. Okay, so this is obviously also a mistake. Shit. Would you be so kind and just run? I mean, how do I free the socket? Free the port? Ah, my God, please. Okay, now it runs. Unsupported HTTP/1 subversion in response. So is it that it writes before? Oh no, so now it got some error. That is also bad. Okay. Wonder where the error comes from. Function flushes the stream pointing to my stream and closes the underlying file descriptor. Ooh, it closes the file descriptor? Oh, that might not be what we actually want. Okay. Okay, so let's try to break. No. Right response. Let's break at 90. Run. So we get here, print the message, body. So this is 0. Should, okay, so this closes it. Unsupported HTTP/1 subversion in response. Okay, so this is something I don't understand. Why is it 1? Why? Why? Okay, so now it tries to close the client and it's already closed. And And when we fail to close, we just close. Oh, we close the server socket. So this is probably okay. Just close it. If it doesn't work, then yeah, maybe just move on. So now we obviously okay, so this works. GB HTTP server. I wonder why it has this weird behavior. Could return line feed 1.1. It should be, or are we missing a space again? Or did we miss to save this file? I don't know. Oh. My goodness. Okay, so let's just run this and try to make it verbose. Upload unsupported HTTP 1 subversion in response. Could you please just print it out for me? What you did yet? That would be great. So this did work. But this doesn't. Oh, well, obviously because it doesn't. We try to give it a reason, but we never really wrote. We never really wrote the okay. So yeah, that's obviously a little stupid. Okay, stir. Okay, stir. So this is obviously just 3, but do we have it somewhere? Okay, stir lang. Okay, stir length. I wonder why it does do this. So const expr car. Okay, stir 200. Okay, stir length. Or just a status code length. Status code length. I think we have that somewhere. Okay, no, we had already we only have it here. Okay. Okay, so yeah. Something like a status code status code to stir and this is obviously the response status code, and well, this could obviously be a constant pointer. What we could also do is in our HTTP we could say lookup. Okay, so we call it lookup response, but we could say lookup status line. Lookup response. We call it lookup status line. Okay. That is that. So we don't need this. So this would just be lookup or is this string that we look up? Nope. So this is const car star status line lookup status line the status code. Now we put in the status line with, oh no, okay, so we don't, with the corresponding length. So we could say f put s in the status line. The socket stream, and if this is equal to EOF, I think, then return this. Okay, so we don't need this stuff here. I think this is cleaner. And f put as reason socket stream is equal to EOF. Okay. Look up response. Look up. Okay, so we call look up response. Look up status line. Look up response still. Oh, we are in the wrong file. How did that happen? Okay. Okay, so this worked. So we can somehow assemble some response using this. but only for the post requests right now. Yeah, okay. So if we have a get, on the other hand, we just want to close the client socket, not the whole server. And we want probably also the response.header map to be cleared. So now I would like to revisit the hash map or header map, and revisit it with regards to Knut hashing by multiplication. I think it was this one here. Multiplicative hashing. And the first thing we probably want to do is remove this arena. And yeah, we probably have to init it anyway, so but the init cannot fail now. Move this into a constant. I don't know. I think the init cannot fail now. And why? Okay. For this thing, the same. So let's go into the http header map.h. So let's say we have a const expr u32 hash table size, and that is just 128, which is the power of, so 2 to the power of 7, or maybe let's make it 256, so 2 to the power of 8. So size shifts, that would be called q, 2 to the q, no, not 2 to the q, but rather m. So this would be m. So hash m, hash table m, therefore is, or it was, oh, how did they call it? They call it p. So I think some called it p. So the basic idea is basically the basic idea is not to take the modulo, but rather multiplicate with some number that mixes up the bits that Knut supposes is this here. And then we use that number, shift the bits down by some q. Okay, so this is called p here. And then take the bottom p bits. So hash table p is equal to So this would be hash table M. And this is also, this is equal to 256. Or yeah, 256, and this is obviously 8. Let's say m is equal to 2 to the power of p. Okay. And then we go into, okay, so first maybe remove this file. Where is it? I think remove, no, not delete, no. Delete. Okay. HTTP header map. So this is the size. This is the bottom bits we have to extract. And we also need a queue. And this maybe is equal to so the queue's maybe equal to, I don't know what a good number for this is. Or should it be the prime number? I don't know. Okay, so this is amount of write shifts. And then in our HTTP header map.cpp, we calculate. So we don't allocate buckets. We just say in our HTTP header map.h that we don't need an allocator. We have a length, a capacity, we have buckets, but this is now hash table M. Okay. So we don't have to initialize them. This is equal to result buckets. We don't need a capacity. We don't need this. And we don't need this. And obviously this becomes now a void. Okay. So clear goes through all of them. Yeah. And makes them empty. The hash probably has to be optimized a little bit. Optimize this, maybe this is a repetitive series. So maybe the idea is that maybe the factor is a repetitive series, is a finite repetitive series of numbers, such that we can pre-compute it. Okay. So here now we have to derive the key. Derive key. And say it's the U64 hash H and turns it into the key. And it does so by shifting down the number h by hash table q, so that's the divide part, and it also has to Knut number hash. So Knut's a suggestion. No. Can we get somewhere the number Knut hashing? Derive a. So yeah, this is exactly it. We multiply it by some a, and that is the golden ratio, which is golden ratio 1.6. Where, so this is the number. Knut hashing paper. Hash by multiplication. Did they have it in here? So this was the number. Const expr u64, and this is the hash a. So it's h times the hash a shifted over by q, and then it is ANDed with one hash table hash table m minus 1. So this is all ones where we want them, and all zeros. So this is exact. This is the modding here. The fractional part of the real number. So we do this in fixed point. They come up with this number here. Okay. So now we have to basically replace this here. So we hash this. Also, the hash function is quite bad. String hash function. Hash times 33. I've had nice results with, I mean, this is also Stack Overflow. I think my hash function is not very efficient. So this was the one I used. Polynomial rolling hashing. The problem obviously is this here, mod m. String hash function. Is there any better results on hash function for, I mean, which one do they use in Rust, for example? I mean, we could just use so value pointer. So let's just use xi. Horner's rule. HS with n+1 iterations. Horner's rule. What is Horner's rule? Horner's rule. It's x, some x. character at n. Okay, so let's maybe just use that one. So this is just we started value length I is greater than or equal to value length. No, greater than or equal to 0, and so value length -1. We don't need this. The value pointer is greater than or equal to value pointer plus the value pointer. And we also just want to get the last three. So last C so this is the last character -1, so okay, so let's say this last pointer car star the value pointer plus value length -1. Okay, so now we want the last three. The last three, which is let's call this also the hash p. So let's say the U64 age is equal to 0, or more or less age is equal to star last pointer plus equals this hash p times this plus hash p times age plus star last pointer minus minus. Let's do it like this. So it also depends on the length. If the length is not, oh, okay, so this is also something we have to consider. So length, min length is equal to U32 value, or more like U size, U32. Value length, oh, it's equal to 3. And if value length is less than min length, value min length equal to value length and then for int I is equal to 0, I is less than min length plus I. Set last pointer to this and minus last pointer. We set the hash. Hash to be this. Now u64 h is equal to 0. And then we say h is equal to the hash p times the h plus last pointer. So the first one is just so the first one is just the star last pointer. Ensure to not oh man, I'm typing. Oh my goodness, help me. And the caller has to ensure that this function is not called with a string of length 0. Okay, so initially this is this, and then we have to decrement, of course. At first dereference and then decrement C++. Okay, so maybe we just do this. Okay. -1. We do this, and we return h. So this should be faster. So we hash this, then we say derive key from the hash. And this is also an AND with the hash table m -1. Hash table m This is also an AND with the hash table m-1. So do we even have to do this at this point? Record position. I mean, this is already the key. Wait a second. I thought... No. So this is correct. So the key is already... So this is... This is part of the hashing. So why don't we just use this instead? So when we call hash, it's already in between the two. Haza? What? So I don't know if we are messing up our table right now. Here obviously we have to do it. The record position is the probe bucket key. No, why do we... This is... Because this should not be required in this case. If the record position is less than 0, how can this even be? Are they initialized with... Wait a second, what have I done here? -1? Why would the record position be less than 0? If we encounter the same field value, we just insert another entry. What was it before? Oh, it could be negative. Is this correct? Okay, so the position... Oh, it's the distance. So this is the distance to the initial bucket. I see. Is it? So yeah. So this is the initial bucket. This cannot be negative. How would this be negative? No. No. So this should just be the key, I guess. So when we say this here, This is just something that we store, and it's already inside of the bounds of our hash table. Then we don't have to do this, I guess. So here, we just get the key. Why would this be negative? I don't get it. So this, the probe bucket is the one that we are actually, that we are probing. Why would this be negative? Okay, so this is obviously this is also not correct, is it? Record. So this has to be the distance from the initial bucket. So this would be the initial bucket. And where are we now? We are, well, I don't know. So can we infer how far? What? So from this point, we would have to infer how far this thing is from its initial bucket. Okay. So this is the actual position. So the actual position is what now? We don't know that. We don't know what the actual position right now is it? So this was the original one. But what is the actual one? So this should be, yeah, how do we know? Yeah, obviously there is an error somewhere. And I think git diff source http header map .cpp. Okay, so let's see if we had deleted something. Inside insert. No. So the probe bucket obviously has a position. So this would be something like current position. This would be header map buckets. So this is the first one, this probe bucket minus this. And obviously now we have to check. So let's go into Excalibur. I could just delete everything. So let's go here. Let's say we have an array. The mic's a little annoying. So let's say this was our initial. The initial bucket, and here we landed. So this is the actual bucket. So now the distance would be 1, 2, 3, 4, 5. So it's 1 to 3. So actual position. So if the probe bucket key is greater than actual position, then we say, so we have some record position. The record position is equal to the probe bucket key. No, so the difference. So if we subtract actual minus the initial, we would in this case get 1 minus 3, so that's -2. If it's negative, we just add 7. Okay, so record position is equal to probe bucket key minus actual, no, the other way around, isn't it? Yes. So actual position minus probe bucket key. And if record position is less than 0, then we say record position plus equals hash table m. Calculate the distance to the initial bucket using pointers. Okay. So now obviously, probably, there's, so we don't need the table cap, we don't need to do this here. We have to do and hash table m minus 1. So this also uses the key, so oh, this is also wrong. Should use the location. Oh. So many bugs in this code. Nice. We don't need this anymore. We don't need this. We just ended with hash table m minus 1. And also this uses location. This is completely wrong. Okay. Oh my goodness. Digests. Okay. We assume that this is already in there. Hash table m -1. So if we would have a collision in this case, we would be, all bets were off. All bets would have been off. Okay. So same thing here. We don't do this. I mean, we could do it. Hash table -1. Also in here. Holy shit. Okay. Table cap. Don't think we need it anywhere. Okay. So now in our HTTP header map .h, this is a void now. It doesn't take any arguments. Oops. Okay, capacity. Obviously it doesn't have a capacity anymore. Hash table m. It doesn't have an allocator anymore. Horner constant, maybe. U8. Horner constant. Okay. And also now I mean, we could say that this is a const expr hash. So this would work. So it doesn't have to be in here, I guess. But I don't know. Comp time hash. I don't know if this works. So hash was not declared in the scope. Okay, so so maybe we have to put this thing into the header file. Doesn't work. Okay, so this is kind of... So it expects a string. That is kind of unfortunate. We could also use it, make it more generic, but we could also make it more generic. Yeah, but I don't know. So let's just, I think we already have these strings here. So this is the transfer code encoding string. So this is the host header string. I don't know if this works, so let's just try. Content length string and the const okay, so that works. Can we also cast it here? Okay, so we can. So this will probably crash. I'm pretty sure it will. So maybe we go into 202. Right, 202, run. P request. Ooh. Okay, so this is just uninitialized memory, I guess. Hopefully it's just uninitialized memory. Oh, yeah. I mean, in init, we set them... Oh. I think in init we already... Oh, so this is also something we don't need. In init, yeah, we set them all to empty, so that should be fine. Oh no, oh no. Oh, so this is also a bug, right response. So the HTTP server won't run. Come on. Okay, so now it runs. Okay, so print parse HTTP, no, request dot header map. Do we have something? LD Linux? Ooh, okay. So this could be anything. So is there any okay. So this is just pointing into uninitialized memory. Okay, so now it should be set. Okay, so now there is something that looks field value, this initialized. So this is kind of works. Okay, so this is a little annoying actually. So that worked. Scheiße. So if anyone knows how we fix this, it would be great. Oh my goodness, just this gesture control of this camera, man, it's so annoying. Okay, so now it works. Maybe not make it verbose. Does it show up anywhere? Okay, so I think, but when closing it doesn't work anymore. Okay. closed client socket should not close. Yeah, if we can't close the client socket, it shouldn't close the server. Okay, so I don't really know what's going on here. Somehow this should not close the server. But I mean on SIGINT, this thing is closed. Or should be closed. Automatically. I don't know. Yeah, so now, yeah. So now it closes the server socket. Shouldn't close. Only if it's -1. I don't know. I haven't really figured out how to do this. Error handling properly. So there might be an error that the socket is not available or something, or that the server socket closed. Yeah, we don't have that at the moment. So that works. Now it does work. Oh my god. Okay, so it's what? I don't know. So the error handling is pretty bad. So what is next? We made our header map a little more hard-coded, which may or may not be good. We made the table size a power of 2 such that we can just cut off the bits or take the bottom bits without having to do a modulo. Yeah. Hopefully fix the bug with this one. I think it's time for some tea, I guess. I'm thirsty. So, yeah. I think I'm getting some tea. Coming back and continuing. So I think what we want to continue with is the get method and getting actually some content. Getting some content, so reading files and serving content. So that was actually something I needed. I like the camera, but this gesture control is just so annoying. Okay. So. We can serve requests now, but there's no content. Especially, we can only serve post requests. That isn't very helpful at the moment. So when we want to handle a get request, we definitely have to check the target. And well, first of all, we could basically try and make a hard-coded response and see if it works. And for this, we probably, we also need, let's say we just introduce some variables, some content, const expr global content, just to see if it works or not. Should we do it this way? I think we implement this side first. So we have some file cache that is probably a hash map as well. Is it? Okay, so but this memory would have to be externally managed. Yeah, maybe we just have a file cache. File cache. And the HTTP request probably has a recast target, which is a string. So we try to get the corresponding file with the file cache. So if we get this request target sorry, if we get this, then well, we set the result status code to OK, set the results reason to null, result message body is equal to null as well. Well, no, the message body is now so this has to be a pointer now. So the message body is a string. Content? No. Message body. Okay, so this obviously is now equal to the message body. So this becomes a void. So what we're trying to implement is just static file serving. Nothing fancy. Okay. So if that is the case, we just, I don't know the status code. Bad request. We just pick that for now to do. Figure out the appropriate status code. Bad request, null. Okay. And we also want to insert, just like here, not the 0 length string. So this is where it gets tricky. We have to now convert thought I heard something. We have to now convert the actual length of the message body into a string. So that would be u32 or usize to string of the message body dot length, and it probably would need an allocator. And then we would have the car star. No, it has to be a string. It doesn't really have to be a string. Usize to stir. I mean, it can be a string. Content length. And we want to insert content length value. So now we have to implement this. And also, this probably returns the number of allocations. Yeah. So this use has to stir probably in some string library. And maybe just return 1, return 0. This is probably the amount of allocations we do. So we don't have such an allocator right now, but obviously we have to allocate here. And we can free it after sending the response. So this is why I want to use the stack allocator on a sub arena that is just for strings. I mean, this could be very small. We could also have some memory. I mean, what is the maximum content length? I don't even know. But I think we have to do something like that. So this is getting inserted. And after that, we're basically done. Yeah. So if we had a file cache, that has all the memory in it. I mean, also we could in this case, when we're using HTML files, it doesn't really work. It doesn't really work because the hashing doesn't really work because the last 3 characters are all the same. Yeah. And if the last 3 characters are all the same, then it doesn't really make sense at all to do it. Okay, so we could either have them in a cache that has all the memory. So we could either have a cache that looks something like this. The file name, let's say index.html, that maps to directly the content. That would be possible. So this would be something like string to string. And again, this would be allocated memory. Or what we could do is we could say at startup we have a folder. We have a folder with entries, and for each entry, let's say index.html, we just make an mmap into that, and this gives us some handle, some pointer into that memory, and the operating system decides to whether or not this is in our memory or on disk or whatever. Now, kind of like this approach here. And I think we do it like this. And for this, we probably abuse our string type as well, because it's just a fat pointer, our string. So this pointer we store in a string with the length. Yeah. So at startup, yeah, so what do? We probably first introduce a new file that is called filecache.cpp and save it, and filecache.h, and pound define if not defined, filecache h, we define it, define and if. Okay, and this file cache, we probably need a struct. A lot of constants again. Yeah, this probably has a struct file handle, which is the pointer and some size. So this is basically the string type. And this has a length and a file handle, some amount of file handles that is probably configurable. Yeah, I don't know. Maybe we say 200. No. Let's say we can have 16 static files. So let's say a const expr u8 or I don't know, max static files. You can only have this many max static files. Okay, maybe we call this the file cache m, which is kind of not very nice. So max static files 16. And probably build cache or something like that. Build cache, and this probably gets a dir end. I don't quite remember how it was. Was it like this? Dir end. Reader. Yes. And a file cache. This can probably fail, so I16. We can build the cache. Probably init. And clear. And yeah, obviously maybe we only need the build cache, which uses the insert, but let's say we have an insert as well. And we insert obviously so if we have 16 entries, I mean, if we have 16 entries, we could determine a perfect hash function at the very beginning and just have this thing sitting there. That would be something we could do. Or maybe we just do probing for the entire table because it's just 16 entries. Or we make it a linked list, but then we would also need an allocator, but that memory can stay forever. Nah. Linked list is probably a bad idea. Okay. So it should store the file name with it. So car star and the file handle. Yeah, we don't really need this push thing here. This is get Par star. No, it's more like get string. String star and put the file handle result in here. Then we also need a stack allocator. So we also need a stack allocator. This one needs a size and so the stack allocator also needs some way of allocating. Or does it? I mean, it does, because it has to have some way of keeping track. So if not defined, stack allocator h define, and if oops. So 1 second. Okay. So the problem with the stack allocator is that it needs some size for internal purposes of managing its stack. But that's not really an issue. Yeah, because when we pop, we probably pop the whole stack item. Okay, let's try to work this out. So we probably have a struct stack allocator, and the stack probably just has the top, or how do we call it, the tail, the tail, and the tail is obviously some item. So allocator item, and does a stack need a head? I don't think so. Or we just call it head, I don't know. This is an allocator item. And obviously a start header, which is a void star, and a size. Okay. So an item, or maybe just call it item, I don't know. This item has obviously a size, so some length. And that probably includes the item as well. So yeah, and some adder. So void star adder start. So when we deallocate, we have to decrement by the size of the item as well. So yeah, that shouldn't be a problem. So init stack allocator with a void star start and a size. You can also destroy this completely. Or reset. And we could say push. So this is an I16 push and pop. And we can push not an item, but rather some size, so usize length. And this returns a void star. And we can pop, which is just the stack allocator. I mean, this can be a void. I don't know. Okay, so let's first make the stack allocator work. So init alloc start. Do we call it adder? I like, so let's call it adder. I like that name a little more. Okay. So alloc adder is equal to adder. Alloc length is equal to length, and probably alloc head is equal to null. Okay, so we try to push. So the next items basically so the next item adder say void, maybe void star next item is equal to alloc length, no, alloc head, and it's its adder, it obviously needs a head if so head, let's say item star head is equal to alloc head if head next items alloc head adder, so it's the it's head adder plus head length. So this is where the next item starts. So the item adder, which is a void star, is equal to next item plus 1. This is where it starts. And cast it to a void star. So maybe this is the inner adder. Next, maybe next item adder is equal to this, and next item length is equal to length, and this is only possible if so we should check for overflows here. Maybe we specify alloc end is equal maybe we do this adder plus length. Maybe we store the end adder. Okay, if next item adder plus length is greater than, is less than the alloc and adder, then we can push onto this thing. Let's say it's greater than or equal to this, then we return 0, -1. If this is less, then we can say return, we say the head, so alloc head is equal to next item. And we also need to track the previous item, item star previous, and we say so the next item previous is equal to alloc head. Alloc head is equal to this. And we return next item adder. So if there's no head, this is basically the alloc adder plus no. do it like this. Return -1. It's the same thing. So this is basically the same thing. Return void star. So I think this works. And when we pop, oh, this is allocate, and we call this free. If head is equal to alloc head, if there is a head, then we want to what if there's no head? Okay, so if there is a head, and if head has a previous, then I think we just set the head to previous, isn't it? Alloc head is equal to head previous. If there is no head, if there is no previous, else alloc head is equal to null. Okay. I think this is it. Not so sure. That would be saying alloc head is equal to null. So that would start at the very beginning. Okay. So this, I think, would work. So now we have a stack allocator. Stack allocator.h. Include types. This obviously depends on the stack allocator now. Okay. Okay, so now we have the stack allocator. Let's review this. So if we have a head, so the basic idea is we have some start adder. We have some address into some memory, and when we push something onto this, then we use this first for this first few bytes for the item that holds the length, that holds the start adder, and the previous. Oh, so if there's no head, we also want to say that the previous, yeah, so this should work because this should be null in that case. Okay, so, and then we set, so this thing will now look like, so let's say this is 0x0, and this will now be, its start adder would be 0x0 plus the size of an item. So this here, oh shit. And this would be its length. And if we pop, let's say we have another item, we just set, so this is the head now. Length and previous. So this now, this previous points now to this, and we say the head is now equal to this. So we, when we push next time, we push onto adder, which is this here, plus length, and that would be this. So we override this. That's okay. So this should work, I guess. Okay. So I don't quite remember where we used this. I think it was in our main. Okay, so here we also have to say this is allocate, this is free, and we also have reset. This now depends on the stack allocator as well. Stack allocator. Okay. Let's throw a little const expert in here. Stack allocator. So this thing okay, so use size to stir, something we can implement now. So that would be car star use size to stir. And that is a use size n. Okay. Integer to string. Should we take Let's see how they did it. This is test. Man, where's your algorithm? Is it in the header file? Log 10 characteristic. Does it take the ln? Holy shit. CLZ to number of decimal digits. Yeah, we need the number of digits. So what did they do? Index into this array. Yeah, okay. Count left 0. So does it only... Count leading zeros. So it counts the leading zeros. Then it indexes. Yeah, then it indexes it. Power of 10. Okay. Count leading zeros. And this returns count leading zeros to number of decimal digits. So that does that work? Okay, I see. So let's make maybe make a string.cpp and a string.h. So that's kind of nice, I guess. I like that. So if not define string h, define string h, and if. So for each, so we count the leading zeros with some built-in and with some intrinsic, and then we can derive from that the number of decimals for each of these. And then well, it's packed into a slice. Okay, so this is just some different things. And then power of 10. I mean, I just want the number of decimals, I guess. This is something we would need as a table. So this would be so this is a const expr include types. So this is basically a map or a table that maps all of the different leading zero counts to that maps all of the different leading zero counts to the number of decimals that that specific number has. So leading zero count decimal and decimals table. Leading zero count and decimals table. Yeah. Usize to Esther. And it takes a usize. Count leading zero. So this probably only works on x86, but that's fine. Count leading zero count built in. Count leading zero. Okay. So go into the string .cpp. No. Copy this, paste. And obviously this needs an allocator as well. So stack allocator. We'd have to verify that, but yeah. So this is the alloc, and this is the, let's call it x. And obviously that is something we forgot here as well, to include the stack allocator. And here we have to include the string.h. So this, now we have to count the leading zeros. That is leading zero count string.h and decimals table. So this would be built in leading zero count CLZ, count leading zeros. Build and seal Z. Maybe that works. So what does that? An int. We index that. And then return that. No. So this is, I use U8 and decimals. Now we have to allocate these many. So allocate with the alloc and decimals times the size of a car. That is a car star, our buffer. And now we have to basically divide by 10 repeatedly. And decimals to the null byte. Oh no. I think this should return a string, doesn't it? So this is not even, call it buffer, and then I think digits in ASCII. It's 2 times val. What the fuck? Okay, so I think we just divide by 10 and keep the remainder. Don't we? So that might actually be something we want to do. So quotient is equal to try to x over 10 and maybe float. No, I don't know which numbers are storable here, and if they are very large, this probably screws us up. So let's just say it's a U32 quotient. This is over 10. And this is just, so the remainder is equal to, this is a quotient, this is n, this is n x minus 10 times n. So we repeatedly divide by 10. So for and I is equal to 0, I is less than n decimals. So this is something. Plus I, we divide by 10, we get the remainder. And this is this has to be the number that, so when we divide by 10, let's say we have 108. We divide it by 10, that would be 10. And 10 times 10 is 100, 108. So this is 8. So this is the number that we have to put there. So maybe, so we add just the 0. So we say buffer at, oh no. Char star buffer end, buffer plus n decimals, -1, minus buffer end, star buffer end is equal to remainder plus, this has to be a U8 plus the 0. Okay. Return. String star results. Results pointer is equal to buffer. Results length is equal to n decimals. Okay, I have no idea if this works. Obviously we have to go into the makefile now and replace mem with string. And also this depends now on the string.o. Exactly. So we now need the string.h. And usize. Yeah, it's a usize. It has to be a usize. So string, let's say it's a usize to stir. Usize. This has to be a U8. So this doesn't return a car star, but a void, and it takes a string. Oh. Okay. And string content length value content length value. Okay. This returns a 1. So when we write that response, so now obviously we need a stack allocator. Stack allocator stack mem. Or this is more like our string mem. String memory. And let's say we want to allocate using our arena, and this should be void star -1. Okay. So if allocate arena, and how big should it be? I don't know. So this is probably, so this is 1 kilobyte, so this is 1 megabyte, maybe half a meg. So let's say const expr usize memory limit times 4 arena memory limit, and let's say our string memory limit is maybe like 1 megabyte, I don't know. So we allocate our adder So let's see, how does did work? Yes, okay. So allocate the arena string memory limit. This is our adder. If adder is equal to void star -1, return -1. So this should not happen. Assert adder usize adder is greater than 0. So this should basically never happen. Asserts matter greater than 0. And now we can basically initialize our stack allocator. So init stack allocator with our adder and our string memory limit. Okay, so when we now handle the post request, handle get. So this should now get a stack allocator, and this should get a stack allocator as well. And a file cache. Stack allocator. Okay. We don't need to destroy this. But when we did handle this request here, so int u16 freeze n freeze, we write this response, and then we go for int I is equal to 0, I is less than, and freeze plus I free stack. Okay. Oh. Okay. And the same thing applies to this here. Okay. I'll call it string memory. Pretty sure there are a lot of problems here. So handle the post request. So for now, this is just all zeros. If else. Return 1, return 0. Okay. So this now expects a file cache. Let's just pretend that we have one. strings where so stack allocator and freeze. Assignment of read-only variable socket descriptor. Okay, so this was obviously a mistake. File cache was not declared in scope, of course. So here we have to somehow build the file cache. Build cache. So we have some file cache. File cache. Okay, build the cache. It's not too big of a deal. So if this is equal to -1, return -1. Obviously, we need the file cache in here. File handle. So dir end has not been declared. Dir open. Read dir. So this is dir end. Pound include dir end.h. Okay. Alloc head was not declared in the scope. Null was not declared in the scope. So standard def probably just so pound include standard def.h. Still null. Standard def.h. In stack allocator. Yeah, here we don't need it. Okay. Okay, so the head is obviously just this as well. Pointer of type void star arithmetic, so that's bad. So This is in our stack allocator. So let's cast this to a U8 star. Does it work now? Okay. Next item. Next item should be an item star. So yes. Alloc adder. Cast it to an item star. And then okay. Cast it to an item star. Okay, now we are in string. View size. Expected primary expression before X. What? This seems correct. Expected primary expression? What are you telling me? Okay, so ooh, string. So we probably want to include mem.h. Okay, so that was obviously a mistake. And we want to include the stack allocator. H. Okay, build cache now. File cache. Okay, so there's nothing in here. File cache. Return 0. File cache. So this is the result. And the root dir. So in the make file, we also need something for our file cache that is a string file cache. And we also need it here. Only 16. We also need the types. Does not name a type. Hello? I included it. file cache.h. String has not been declared. Undefined reference to the get. Okay, so get is also nothing we implemented. Don't even know if we need that clear here. The file name. Okay. So it compiles, it probably won't work. But I have to go and pee. See you. Okay. So I don't know if we should continue with implementing this file cache now, or if we should stop for today, because I have to do some things. I mean, we can try to make it work. We can try to implement the file cache. Yeah, the file. I mean, the file cache is just. Yeah, we need a length. We need a length. So init sets the file cache length to 0, and yeah, that's it. And clear does the same thing. Get. Oh, clear also has to probably munmap. If we use mmap for these kinds of things, we have to do that. So file handle store handles equal to file cache handles plus handle. I don't really know how we call this. So this is handles, yes. So munmap. So this can fail. If munmap. So what does it return? Does it munmap return value map failed? So if this thing is equal to map failed, return -1. munmap handle pointer. Okay. I think it just takes a pointer. No, it takes also the length. So this is the handle length. Okay. Sets the length to 0 and returns 0. Okay, get. So string. We have to iterate through all of them, which is 16. No, not through all of them, but just how many we have in there. So yeah, like this. And if string equal file name and handle file name. I don't know if this is a reference or not. Then we say return 1 result star result is equal to handle, and that's it. Otherwise we return 0. And now the building of the cache. So reader reader takes a dir. So we don't take a dir, but a dir, not a dir end, but rather a dir. And reader returns a pointer to a dir end. And okay, so while reader for so let's say dir and current entry reader current entry is equal to this. If not, well, we could also say this is equal to reader and the root dir or static dir. I don't know. Maybe the static dir. And while current entry, we do this. So we could also say that this is not our file cache is this is not a car star, but a car this is a car 256 const expr u16 max file name length 256 max file name length. Okay, so we do this, we get the current entry, and now we have to look at dir end. So this has a D name. What we can do is mem copy or stir and copy. I mean, we could have a string library right now. I don't think we have stir and copy right now. We just have mem copy. To do introduce a proper stirring library for copying. So mem copy, and this is the destination, which is so file handle star current handle result note the caller is to ensure that the file cache has been initialized. Result handles okay, so we make this a for loop int I is equal to 0. Current entry, and I has to be less than max what do I call it? File cache, max static files, max static files. If not current entry, return break. If we have one, we just say okay. Or maybe we could say something like current entry, and we don't need to do this here. So mem copy into the current handle pointer and the we would have to make sure that and this is the file path length. So we'd copy over file path length bytes into the file name, and now we have to mmap. Okay, so we have to actually include that as well. Sys mman. So I think the first one was null. Then the length, which I don't know. We have to. So we have to first get the length of the entire file. That's kind of unfortunate. So what was it called? Fstat. Stat. But for this we would need the entire path. Okay, so we would have to join the paths. Yeah, we would have to join the paths. So this is kind of tricky now. We will do that in a following stream, reading all the files. But we got somewhere today, I guess. Could be better, but I will be online tomorrow, so hopefully we get somewhere. Have a nice evening. Bye.